presentation. And it takes a little bit of time to receive the recorded videos. I will actually upload everything, all the last 3 or 4 lectures, probably by tonight or tomorrow night. Okay, so let me switch to my iPad. This stability is coming from the analysis by von Neumann method. There are different methods, but the one that we use in finite difference, especially in our class, is von Neumann. Stability analysis, and it's all about this amplification factor. So von Neumann defined this stability as to really minimize the error term in the Taylor series, right? So remember the Taylor series has all these different derivation, first order, second order to the terms. At the very end, there is actually an error term, which I may not actually cover that, but there is this error term called O. And of course, because this is an approximation, you should have some sort of error right here. So if you minimize this error, we should have a nice stability. If this is 0, then it's good. But then if the system doesn't converge, then we have some sort of problem. So what we are going to define is our unknown function in the next time steps, right? And I don't talk about the space. That should be fine. Let's say we have 1D or 2D. But then von Neumann defines these future unknown function to be a factor, which is our amplification factor of the unknown function at the current time step. And then he found actually by different type of schemes, this amplification factor has a significant impact on the stability of the finite difference schemes. Okay, in very general way, if we don't talk about different schemes, well, he found that if the absolute value is less than 1, you most probably should have a stable system which is damping. I think I explained a little bit on this. So let's say if this is your input signal, then the output signal or the unknown function is stable and it's damping, right? So you should expect some unknown function less than what you had in initial condition. If this is equal to 1, then this is neutrally stable. That means it's not it's stable and it's not damping, which is nice. And as I mentioned, the damping here is not really about the physics, like if you have an energy loss or diffusion or friction, this is just by the error from the numerical scheme. That's a function of the amplification factor. And if this is larger than 1, then that's the case that you are in trouble. And this is amplifying. So if this is your input signal, then the output signal would be larger, 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 and sometimes it's going to be really crazy at the end. So he found this A is really coming from the Fourier transformation. So I'm not really going into the details. For 1D advection, and this amplification factor is basically different, could be different in different physics, different partial differential equations, we are talking about just 1D advection at this moment. So this A is equal to the velocity times delta t time interval divided by the space interval. If we only talk about these two different schemes of forward in time, backward in space, well, let's just explain the forward space because we covered this first, right? Forward in time, forward in space. Then he found that if v, or velocity, is in the direction of your forward scheme, so let's say this is positive, then the system is going to be unstable. So no matter what is the amplification factor, the system is unstable. But if the velocity is less than, it's negative, or let's say in the opposite direction of the forward scheme, right? Then you may end up with a stable condition. And now it's really talking about this absolute value of the amplification factor, right? And you have these three. So it's not only about the amplification factor, but it's also about how the direction of your velocity field gonna be compared with the direction of the scheme, right? In this case, the direction of our scheme is that at the end we need the goals, let's say if this is our grid, right? For each unknown function, we need to use the next grid, right? Which is, we are really moving in this direction. And then if the velocity is in the same direction as our scheme, then we found that this is going to be unstable. And the same thing almost happened to the forward scheme, but for the backward, forward in time and backward in space. In this case, we are moving in this direction, right? Because in your grid, for this point, you don't need these 2 points, but now you need the same point in the previous time step, but the last point in the previous time step, right? So we are really moving in this direction. Okay, so in forward time, backward in space, it's again the opposite. If velocity now is larger than 0 or is positive, which means it's in this direction, then this is going to be stable. If velocity is less than 0, or let's say the direction is the same as the scheme, then this is going to be unstable. And here actually it depends again on the amplification factor. But it could be stable at least, right? So again, this is really the key. The direction of the velocity should be actually in the opposite direction of your scheme. And that's the case that you could have actually some stable numerical simulation or approximation. Does that make sense? Any question?
Doctor, is this proven?
This
Like,
yes. So for one, the advection, and for the final difference scheme of the first order scheme that we are using, this is proven, yes. And we will prove this in the Excel file.
okay.
Okay. So now let me switch to my desktop to go over the Excel file. And if you haven't sent me the example, you can still send the example to me so I can send you the feedback by Monday. Okay, can you see my screen?
Yes, we can.
Yes. Okay, great. So this is what I did for the smaller space interval. Nothing really has changed except that we need a large number of grids, right? We need 100 number of grids in space, and every space interval is just 1 meter. You can play with all these variable like delta T, V, and everything. So this is our input signal, or let's say the initial concentration of the chemicals in the system. At 50, it was the maximum, which was not 1, right? And then, so I write the code to calculate the unknown function. We are using the same space in the previous time step and the next space, which is forward, right? So this is FDFS. And in this case, we have been able to calculate all the values. So now this is a forward time, forward space, let's say positive direction, right? And our velocity is also positive, right? So let's see what we have. We have a constant, well, this is our amplification factor. So let's see what would happen in this case. The velocity is positive, right? And our scheme is also positive. So we are actually expecting to have an unstable system, and it is unstable, right? So as you see, this is my input signal. After a few seconds of simulation, let's put this at 15 seconds, right? I got some numbers which is larger than 1, which shouldn't happen physically, right? And even I got some negative numbers, which could not happen because we're talking about a concentration which could not be negative. But if I put this as negative 0.5, right? So in this case, the direction of the velocity is in opposite of my forward scheme. Now, you're going to see that the system could be stable, but my amplification factor is now larger than 1, right? So if I move this, again, this could be unstable. You see that we got really high values, significant values that shouldn't be correct. But now let's try to decrease the amplification factor to lower than 1. So in this case, my velocity is 0.5. The amplification factor is dependent on dt. If I put this as 2, then amplification factor is 1. And we found that if this is equal to 1, we have an unconditional stable condition. And that is true, right? My concentration doesn't change. It's just moving from right to left with the direction of the velocity, which is negative. So this is the velocity field, right? And if I move this to the larger time values, you're going to see that this is oops, nicely moving, right? There is no amplification, there is no damping. This is exactly what we would expect from a pure advection problem because we don't have any diffusion. There is no energy loss in the system. Okay, so does this make sense? Any question?
So, doctor, you used the periodical boundary condition here, right?
I believe that this is not periodic boundary. Let's see.
Yeah, because I've noticed that the wave showed up from the other side when
Oh yeah,
you
this
kept
this is a
moving.
yeah, this is actually periodic. So and this is how actually you can solve the periodic or define a periodic boundary condition, which is pretty simple. So what you did for for a closed boundary condition, remember, right? We define the ghost points right here. And these are just arbitrary imaginary numbers. We borrow the values from the previous, oh no, the function, right? Which is known from the initial condition. So we are just borrowing, or let's say, we are mirroring the value to the ghost point. What you need to do for the periodic boundary condition is just coming from the physics of the periodic condition, right? In a periodic condition, if let's say this is your input signal and the input signal passes through the system, we would expect that everything that goes out, it should goes in from the other side, right? This is actually the definition of the periodic boundary condition. And by that, I just do a very simple trick. So now, instead of borrowing the value from the previous time step, I just connect this ghost point to what I have at the beginning, right? At the first point. So everything that goes here now it's going to be mirrored to the last point. Everything goes out, everything goes in, right? So if I move these to the larger time steps, at some point you see that the signal is going to here, but then you should expect to see it's coming actually to the boundary again, right? So let me go down more. So this is how you really can define a periodic boundary condition, which could give you a lot of freedom and flexibility to minimize the size of the space and to simulate really large, simulations for really the domains that you like to simulate for a really large domain, but you don't want to necessarily define the large domain, right? So you just truncate the system into the small system, but then define a periodic boundary condition. Any question? And I think Khalil, you did this. You had the idea, but then when I tried your Excel file, it didn't really work.
Yeah, I did the same idea.
Okay,
Yeah.
good. And I have to double check all the other submissions. I'm not pretty sure from for the others, but I think this is what I remember at least. Okay, no question. Are we good to go for the next topic? Okay, so I think we are just nine in the group, so I don't need a survey. But just on the chat panel, can you put a number from 0 to 100 and give me your grade, let's say in MATLAB? How familiar are you with MATLAB from 0 to 100? Just a simple question. Just want to get some insight from you. Okay. Yeah, I need all your inputs. Okay, good. Okay, nice. So you have everything from 0 to 50 and a little bit higher, 60. Okay, good. So MATLAB is really huge, but the functions and the options that we use are really limited in this course. So I've been working with MATLAB in the last 10 years or so, and I would say I know about MATLAB maybe 60, 70%, but it's a lot of functions and tools. Um, but second question, everyone you have MATLAB on your desktops and systems? And if not, just let me know. Okay. Okay, good. So it's nice because we can actually go over MATLAB just step by step. Okay, good. So then and okay, you can actually work with me. So we can work on MATLAB together. And I increase the font. I hope that this is readable. Otherwise, I can actually increase of the fonts more. Is this fine? Can you read the fonts or because my screen is really large?
Yes, that's fine.
Okay. Okay, it's blurry. Okay, I think that it's blurry maybe because of the internet. Otherwise, it shouldn't be blurry. But let me increase the font a little bit more. It may help. Not pretty sure. Uh, Put it at 24. Okay, this is good. Anyway, so let's open up your MATLAB. Once you open this up, you're gonna see actually three. As I see that your grades are not really hard, so probably let's just do everything together. Once you open the MATLAB, you're gonna see actually three different spaces, as I see. The preferences or the setup of your MATLAB could be a little bit different from mine, but most probably you should see MATLAB in this format. So for three different um, space, this is space called command window. So this is going to display any calculation that you do during your codes, or even you can use the command window to do very simple calculation. Let's say 2 plus 2, it's going to show you the result, which is 4. Or you can even define a variable, let's say a is equal to 4. It's going to display everything. So this is a command window. Here you have the workspace. So on the workspace, let me actually see my iPad so I can check what you see as well. Okay. Okay, so in the workspace, everything that you calculate gonna be stored, right? So here, for example, you have the answer for the first calculation, but here A is a variable that I defined, and the value is 4. Even you can actually open up the variable if you just double click on this, and you can see the value. So here, because my variable is just one value, it has one cell, right? And everything will be stored in the format of the metrics, unless you define this in and at a different format like a text or anything else. So this is about the workspace. And then you have this editor, which is the space that you are going to use to write your code. Okay. So what I usually do is actually to split these spaces. So I'm gonna just grab this space just by the left click, right? And then put it somewhere else. So in this case, I can split my, should be somewhere. Let's see. Where did it go? Okay, so it's here. Yeah, I think on the other option, let's see what I did. Let's close. That's that. Having all these, at least two of these spaces or windows back to back or side to side, that will give you some freedom. Okay, let's see what is this. Unrecognized function. Okay, maybe I open up an old version. Okay, I have a 2022. This was a 2019. Okay, go down. Let's just open up my last version of Flight. Okay, so I have the workspace, I have the command window. If I click the new script, it is going to here, so I can actually undock. If I undock this, okay, now I have a separate window for the editor, right? So the editor is the space that you write the code. So what I do is just split my windows into two different sections, right? So I have an editor here. This is a workspace. This is my command window. But again, up to you. If you prefer to have everything inside one window, that should be fine. All right, let's see. And now we are trying to write our 1D advection in the MATLAB.
Hi, I'm
Mhm.
sorry. I don't
Sure.
have the editor part.
Okay, if you don't have it in the home space, okay, just click on new script. So go to the home, it
Okay.
might be on, and then click on new script. It should show up.
Okay, I think I have it. Thank you.
Okay, nice. Any other question? Okay, let me open up my last code so I can go over this. Okay. So what I usually do when I write the code, well, first of all, just save the code, right? And name the code as you like. So this is going to be a 1D advection, for example, FDFS. So you have a file. Okay, so you cannot put one at the beginning. I think that was a problem. So I just gonna say this is 1D, sorry, FDFS 1D. Okay, inside the editor, you have a lot of different syntax and codes that you can put. If you put this percentage symbol, then your code doesn't count as a calculation, it's just a text or a reminder, okay? And that's why it turns to green. So for example, if I write, let me start with a equal to 2, right? If I just save this, this is just a simple code. You can simply run this by pushing this button, which is run. So if I run this, you can see the calculation here, right? This is the name of your code or the file, and this is a calculation. A is equal to 2. Okay, now if I write just some text as a reminder for myself, I'm gonna just say this code is FDFS for 1D advection problem. Because later you're gonna generate a lot of different, codes. So if it's nice to have this kind of reminders or text inside your code. And then if I clear the commands, right, this should be cleared. If I push this clear workspace, the workspace is going to be cleared. And this is what I do after each time I run the system, because sometimes the variable is going to be stored here and they may actually make some trouble in your new calculation. So now if I run again, you don't see this text inside your command window or the workspace. This is just a text, right? Or some hint. Okay, now this is how I split different sections in the code. Again, I'm gonna use the percentage symbol, and I just say this is the section for my input parameters. And maybe a few dash points just to separate the sections, right? Okay, so what are my input parameters for the 1D advection? You're going to just copy and paste everything that you had kind of in Excel to, or transfer everything to MATLAB, right? First, we need to define the velocity. So V is equal to, let's say 0.5, right? And now once I write this, the code, again, I'm gonna just put some note here, just as a reminder that this is velocity. So next time that I open the code, I can really understand everything. And the units is in meter per second. Right? And it doesn't matter what you write here because it doesn't count as a calculation, right? So if I run the code again, okay, it just saying this is my simple code. Velocity is 0.5. Even I can click on this matrix of velocity, which should have only one cell, right? And it shows me the value. So let's close this again. I don't need the workspace. Okay, clear commands, clear workspace. Okay, sometimes you have a lot of calculation. So again, if I run this, you're gonna see everything in the command window, right? So sometimes you don't like to see all these calculations through the command window because you have a lot of lines. In order to solve this issue, you can just put a semicolon at the end of your calculation. Okay, so if you put this semicolon, then let's see what would happen. If I clear command clear workspace, I run the test. I don't see anything here in the command window, but your variable has been stored in the workspace, right? So you should be fine. Okay, so this is velocity meter per second, and you can go on, right? When you write the code in MATLAB, just try to write the code in in a way that if next time you like to change anything in the input variable, it should also work for you, right? So for example, in our problem, the length of the system was 100, right? So we can change this to 200, 300, but what if the starting point of my problem was not at 0? Let's say if it was at minus 100 meter and then ended up at 100 meters. So this is actually how I write my code, and you can write it in different ways, but I would define the minimum um, geometry of my system as x mean, and this is 0. Again, semicolon. So this is my minimum value of x in meter, right? And now I'm gonna define a maximum of x. Well, from the problem that we have been working on, it was 100, right? And again, code, the text, maximum value of x in meter. So really you can define the length now, right? The length later can be calculated as simply x max minus x min. Even you don't need the brackets, right? So this is the length. And let's just, every time that I write a few number of lines, I'm gonna try the code, right? To debug the code if anything is going wrong. So let's see, velocity is 0.5 meter per second, length is 100, x min is 100, x min is 0, x max is 100, right? And of course, this is correct. This is just simple math. Okay, next, we are going to define the space interval. So let's call this dx, and let's just pick 1 at this moment, right? When you have the code, it's really easy to play with these things. In Excel file, you have to, grab the mouse, and every time you need to increase the number of cells, which is really time consuming. But here, everything happened really fast and easy. Okay, and this is my delta x, again in meter. Okay, what else we have? The time of the simulation, and this is the maximum time that we are trying to simulate. So let's call this a Tmax. So in our case, I think we pick 15. And again, don't forget to write the units, because everything that we define here, you don't see the unit, but the unit is really coming from the physics. So the units of each of these variables should be compatible with your physics. So this is max value of time simulation in seconds. And now you need also the time interval, right? Let's call this dt. In our case, we pick 3 time intervals, again in second. Okay, I think we have defined everything, right? The other was let me know if I miss anything. Okay, these are the input variables. You can actually calculate a few things here. It's one thing is about the length. The other thing probably you can also define is alpha, or the amplification factor. Let's call this amp, which is simply v times dt divided by dx. Okay, again, I'm gonna save file, clear command, clear window, and rerun the code to see if we have everything. Okay, is there anyone who have a trouble to do whatever I'm doing here in my MATLAB?
Yeah, I don't think that mine is like running. I don't know if I'm like doing it right, but it's not popping up in like the workspace part.
Okay. Can you share your screen?
Yeah.
Okay.
So like when we first logged on, we were writing this down here. It was popping up over here, but like up here it's not.
Yeah, so the problem here is that you have a incompleted line of line 12. Okay. So
Yeah.
can you run it for now? Let's see what would you get.
Is it this button right here? Up here?
No, that one is a little bit different. It's gonna give you the time too, so it's a little bit more time consuming. Let's see.
Yeah, I don't see like the run button on mine.
Okay, I'm gonna show you just a second.
You can go to editor, I think.
Yes, yeah, on the top, go to the editor. On the very
Where?
top. Yeah, on the very top of your, yeah, go to the editor and now click on run.
Okay.
And that's why I'm just suggesting you can have actually two different sections for the editor and the workspace. Yeah, you cannot have a space actually in your name, so it will not allow you to save the name. So just run it again. Okay, now okay, click on the save as or go to the yeah on the bottom. Okay, save as. Let's pick a different name or remove the space. Okay, now save it. Okay, now run the code. Okay, so you see the error is that you have an incomplete line of line 12, right? Let's just remove line 12 for now. Okay, and run. You're
Okay.
fine, right? So you have everything.
Thank you.
Yep, no problem.
Professor,
Sure.
I have a short question.
Yes.
In the screen we just saw of the editor, there was a vertical line on the editor, uh, about 3/4 from the left side.
Yes,
What
yes.
is the purpose and why is that line and what is the purpose of that?
Well, you don't actually, sometimes MATLAB would not allow you to exceed the length of your code to exceed actually that line, right? So you should have your code less than that border that you mentioned, and if it exceeds that line, you can actually go to the next line and then write your code.
So we
Okay.
should consciously make an effort to press enter whenever we try to cross that line.
Yes, or let's say you have a very long equation, right? You have to actually split your equation to subdivisions and write your equation in a way that it would not exceed that border.
All right, thank you very much.
Yeah. In my screen, I increase the font so you're not able to see that line, but it's somewhere on the right-hand side of my screen. Okay, let's see. And you see my screen again, right? Just to double check.
Yes, doctor, we can see it.
Okay, good. So let me move on. This is the amplification factor that we defined, right? And let's see what is the value now. It is 1.5, right? Okay, next go to the important part of our code, which is the discretization. And if you can learn this part, you should have a lot more easier life in the next, not this one, few lectures. All right, so let's call this discretization. And this small section that you're gonna see is gonna work as what you really did in Excel to create all those cells. everything here, this is my input parameters, right? This is going to be discretization. Okay, so we have to discretize our space. So in order to do that, I need the number of data points, right? What I have here is the intervals, which is the delta x, but then depending on the length of your system, you may have different data points, right? So what is the number of data points? Can you tell me? Let's call this nx. Just give me the equation. Length, right? Divided by time interval. So let's say if the length is 100, and let's say if the interval is just 50, how many points I have? The first one, which is the beginning, the last point, which is the last one, right? And because my space interval is just 50, I have to split my length into half. So in general, I have 1, 2, 3 number of grids, right? Or points. So really the equation is just length divided by delta x plus 1, right? Do you have a question, Emery?
Oh, I'm sorry. I didn't know I still have my thing.
No, that's fine. Okay. So let's see if this is working, right? For 50 space interval and 100 of the lengths, right? I have 3 number of grids, right? Which is correct. So if I put this as 1, then I would expect to have 101 number of data in the space, right? Which is 101. Okay, so this is a number of data points in x direction. Remember that we have to find the unknown function on the discrete number of data points, right? This is what we are trying to do. Okay. So for each of these data points, you need to also find the value of x, right? Or let's say the x coordinate of each data point. And this is as easy as this, as you can see. X is equal to x mean to x max. How many, or with what interval with dx. So this simple code that you see here, let's see what is this going to do. Yeah, I'm gonna write something very simple on the command window. So I'm gonna discretize the system from 10 to 100 by every 5 interval. Okay, and let's call this as C, for example. Okay, I'm gonna open up C. So it's going to be, let's see the code, right? This is the code. So my C is now going up from 10 to 100, right? Each 5 interval. Okay, now we're going to use the same strategy to discretize our x, or find the x coordinate for each data point, right? So if I run this code again with a semicolon, let's see what is my x. Okay, 0, which is my first point, 1, 2, 3, 4, up to 100, right? And this is exactly what we are looking for. Okay, now let's look into the ID of each data point, right? I have 1 data, 2, 3. These are really the i's, right? Remember that on our unknown function in discretized form, we had u, I, n plus 1, right? These are really the i's, I1, I2, I3, I4. Okay, so this is my coordinate for the x points. Okay, I actually need another, just one more cell here, and this is really for, I'm gonna put the note, plus delta x for the ghost point, right? Because we are adding one more node to the system, which is for the ghost point. If we are using the forward scheme, the ghost point is on the right-hand side. If I use a backward scheme, I have to actually decrease this by delta x, right? But now I'm just working on a FDFS scheme. Okay, what else? I need the number of time steps. So let's call these n number of time steps. Same thing as what we found for nx. It's basically Tmax, or the length of your grid. We are talking about the time, so this is T space divided by the time interval plus 1, right? Same strategy. And this is number of time steps. Okay, we have almost everything. We can actually initialize our unknown function. So at the very beginning, we can say, okay, my unknown function should be a matrix, right? At the very end. This is a 1D system, but I'm trying to calculate. Let's see if I have this Excel file, right? Let's say this is your unknown function, this entire thing. So you have your X value versus time value, right? So depending on the number of X grid and time grid, the dimension of the matrix would be different. So what is the dimension of the matrix? Number of X points, number of time points, right? So let's put this as NT steps and NX. And if you just write zeros, this is a syntax in MATLAB, or a function in MATLAB. What it does, it just generates a matrix of zeros. So all the values are zeros, but in the size of A times B, right? This is a matrix of A times B. Here, the first size is the number of time steps, the second size is about the space. Okay, so let's run this again. Let's see what is my unknown function now. My unknown function has, okay, all these values, which is for the first time step, right? This is time step 1, 2, 3, 4, 5, 6, and I1, I2, I3, 4, 5, 6 for the X space. But these are all 0 at this moment. This is how you can say I'm initializing the unknown function. Yeah, my unknown function here is about the concentrations, right? Any questions so far? Okay, so I hope that everyone is good. Let's go to this next set or portion. Let's call it set initial conditions. Okay, what is our initial condition? My unknown function is going to be, we have the function, right? It's exponential of negative 0, 1. This was the formula that was in the statement of the problem. X minus 50, and now the X has a meaning, right? It's not just one value, it's changing. It's a variable that we calculated here, coming from 0 to 100. And this is going to be to the power of 2. So this is how we can actually write the power. And sometimes if I just use this symbol, it should be fine, but sometimes you need the point as well. This is a better representative. So I would put point symbol for the power. There we go. But this is not actually working because x is changing, and I'm actually trying. This is the large matrix, right? Remember the system of the composition or the format of U or unknown function. What is the initial condition? The initial condition only applies to the time at the first time interval, right? Because the time is 0. So how to define this? This is how we can actually write the syntax. I'm just trying to specify just the row of the unknown function, which is related to time 0, right? Which is for the first time step. So I just gonna type here. I'm just looking for the unknown function for the first row, but for everything in terms of x. So this colon uh, format or syntax that I put here means everything or all the cells. Okay, so I'm looking for only the first row, but for everything, right? For all the x values. So for example, if I put this as 2, this is what I'm trying to find, right? So if I just type 2 and 2, then I'm referring to this cell, right? So if you just put this colon and 1, again, all these cells in the first row. This is how it works. And this is how we can initialize the system. Initial condition. Okay, let's run the code again. Code is unable to perform assignment because the indices on the left side are not compatible with the size of the right side. Okay. Okay, because we formatted in a different way. Okay, our this has 101, but this has 102. Let's see what is going on. Okay, x is coming from oh, okay, so this is the problem, right? So we have this nx. This is the number of physical points in the system, but you need actually one more for the unknown function. Sorry, for the ghost point, right? So I'm gonna just write as +1 for the ghost point. So the text should be fine if you pass this line, but your code is not. I think that was the case. Okay, now the code is working, right? So again, this is for the ghost point. And this is your U or unknown function, right? This is exactly what you made in the Excel file, but we haven't calculated the unknown function for the next time steps. Any question? Okay, I see a hands on.
Yeah, can you please repeat the last syntax line for exponential? Um,
This one?
Yeah.
This is just a power, right? So if you just put this symbol, right?
Can you like read it out in the entirety? Like it's point, an exponential parenthesis minus 0.01 times. Is it x minus or what? Is
No,
it
no,
something?
yeah, this is minus, right? X minus 50.
50, right?
Yes, and this is from the problem statement, right? This was the
Yeah.
function formula. Yeah,
Yeah.
and then this is to the power of 2.
Okay, I think I might have been missing something. Yeah, it's
Okay.
still saying
Uh-huh.
it has a problem in it. I don't know.
So you mean you
It's
got
saying
an
error.
error when you run the code, or what is the
Yeah,
problem?
in running the code. Yeah.
Okay, it might be from the parentheses or the brackets. Do you have enough brackets? Because if I remove this bracket, then I would get
Oh
an
yeah,
error.
I think it's that probably. Yeah.
Yeah, so
Nope.
then no.
Even without like extra parentheses, it did not work.
Okay, then maybe you can share your screen.
Okay.
And then I will answer to Amary's question.
You seeing my screen?
Yes. Okay, it's not maximized, but probably I can see. Okay, so you have one, two. Okay, the problem is from line 22. Can you
Yep.
maximize or is that line 22?
Yep.
Okay. Yeah, I don't see any problem, but let's see. Expression when calling a function or index. Yeah, I don't see the left hand side. Maybe it's my problem. Let me maximize. Okay, now I see everything. Okay, indexing a variable, use parentheses, otherwise check for mismatch. Okay, you have everything. What is wrong?
I think it's this 102 in one of the unknown matrix is 102.
Oh, so that might be the problem, but I think you fixed that, right?
Yeah, dx.
On line 17, you got to add delta x to x max.
Oh,
Yeah, that was my problem too. I
What
yeah,
was
forgot
that
to
exactly.
again?
You have
You
to add the
you need to
DX.
add a delta x to x max. So just plus delta x. Oh no. Um,
No, that was correct. Okay, then after X max, yeah,
Okay.
just plus dx.
Okay.
Yeah, that's gonna add one more point to as the
Yeah.
ghost point,
Awesome.
right?
Yeah. Now it's
Okay,
solving. Yeah. The
okay, good.
matrix is good. Awesome. Thank you.
Yeah. Okay, now Amaris.
I was having the same problem. I just had to add the DX.
Oh, okay. So it's solved. Good.
Professor,
Sure.
here I have a question which you just described, adding 1 to the uh, delta delta x. If we use a bracket for the whole expression, like nx is equal to bracket, then length divided by dx, then bracket close, and then you add plus 1.
Okay, let me share my screen. Let me see if I understand your question. So you're saying about this line?
I'm saying about line number 18.
18. Okay. Yeah, this line, right?
Uh, just one second. No, sir, line number 19.
19. Okay, right here. So
Yes.
you're saying
So,
that we're gonna put a bracket like this?
uh,
Maybe here. But yeah, but when you write this one for
I'm
X,
sorry, I was actually talking about line number 18.
okay,
So,
18. Okay.
what you just wrote is, I think, what I did also. So, there shouldn't be any difference.
Oh yeah,
Okay.
of course, yeah. This is actually how I format my things just to be neat and clear, right? So I mean, if you're asking if you remove the brackets, what would happen, right?
Yes, because earlier there was no bracket, and when you ran the code, uh, there was some error.
No, I think that was not the case for this one. Let's see. NX is also 101. So no. If you remove the bracket here, it doesn't change anything. But I just prefer to have the brackets to be more clear when you have, the divisions or multiplications. Just this is more clean because I know that okay, I'm just doing the functions,
Uh,
everything first and then add
I
one more.
I have one more question if you don't
Yeah.
mind. About line 18, you are adding dx to that sequence. So here, if you put a bracket before x min and a bracket after x max,
You mean this one, right?
yes, so
No, that's a different story. Okay, that's a different story because what this code is doing is just the code actually needs three variables. So this is my first variable, second, and third. Okay. So if you put a bracket here, so you don't need a bracket here. Okay. If you put a bracket, it's just gonna discretize the entire system and it's gonna add up dx to all of them.
all right, all right. Now I
You don't
understand.
have to do that.
Thank you
Yes.
very much. Yes, I got it now.
Yeah, I mean, I know that it might be confusing, but you need some time to practice different functions to really understand how different syntax or codes work. So this code is really different from what we have here. This is a basic function, right? This is a upper end type of the higher end function that they're gonna do a lot of work for you. Okay, so I hope that makes sense. Um, One more thing that I would like to do here is that, okay, now once you have this unknown function, let's actually plot the unknown function. Okay, let's see. I'm just gonna write plot. This is a function, predefined function MATLAB that's gonna plot 2D type of graphs. So the first variable should be, and when you write here, most probably you should have this line. It's gonna give you some insight, right? It's just telling you, okay, I should have like y line specifications, options, and etc. I'm gonna talk about this help button later, but let's see what would happen now. I need the first variable, which is my x, or the x-axis. My x-axis is basically the x. This is exactly what we did for these graphs, right? This is the x-axis. The y-axis is my time. Okay, so what is the y-axis? Sorry, sometimes the unknown function, right? Unknown function. At this moment, I only have the initial values, which is the first row for everything. Okay, let's run the code one more time. Did I change anything here? Okay, 100, 101, 102. Okay, again, something happened here. Let's see, this is the x. Okay, u is again 102, x is 102. That was no. Okay, incorrect dimensions for erasing matrix of power. Okay, what did I change here? I didn't change anything, right? Think about this. Okay, line 24. That is the problem, but I didn't change anything. This is stretch. Okay, this is 102. X is also 102. Okay, this is a strange message.
Dr. Mawade, it's your power. To power to 2, you should
Yeah.
add the point. You should
I
add
did
the
actually.
point.
I
Okay.
did add, but it didn't work again. Wow. Okay, it's magic. But I think I added the point, but I didn't. I get the error again. So
Yeah.
this was strange. Anyway, okay,
Okay.
thank you. Okay, now let's plot. So clear, clean. Okay, and then this is actually a plot, right? So 50, at the 50, it should be 1, right? And then this is your concentration. You can add a little bit of more syntax here or code to just define the format of your plot. And when you push with this comma, then it's gonna give you, okay, you can actually define the color and different styles. So what you can do is just, if you, let's see, if you just type R as red, okay? So here the R stands for red. If you if you write B, it's gonna be blue, G green, but I like to have a line in red. I would like to have actually my data points, the markers, right? Like in a circular format, and then everything I would like to connect all these data points with a line. So this is really the meaning, red circle markers with a line. So if I now run the code, you see this nice format, right? So I have these markers, everything is connected with a line, and it's also red. Or you can even change it to K, and K here stands for black. So data is now black, right? So you have to be familiar with this format and things. How you should be familiar with this. Well, this is how the help of the MATLAB gonna help. Really, it will be really helpful. So if you push help on this section on top of your home, you have a lot of information here. And of course, the time consuming to go one by one, but you can actually just search on this section, right? I'm gonna just search for plot I don't know why my keyboard doesn't. Okay, now it's working. We have plot, and I would go for the plot 2D, right? Plot 2D. And now you have a lot of information here. So it's just saying that, okay, plot X and Y creates a 2D line plot. This is your X, this is the format of your Y. You can actually define the line in the specification, but what is really helpful is really about these examples, right? So for example, this is a simple plot of X and Y for this function, but now they added actually another line, so you can write it in this format, some other examples, and this is about the format, right? Even you can define these dash points or dash lines. You can change the color. So going over this help, actually, you can have a lot of examples and functions, so you can see how these different syntax or codes really are working. But I will give you a lot of these insights or examples during the class. Okay, any questions so far? Okay, I think we don't have time to go over these approximation, but the next step is really your final difference method approximation. So you need to write a loop function through time and space. So we call this marching, right? If you can write this loop, then you should be able to simulate your unknown function for different steps and different times. So just give you at least the insight of how a for function works. So you can actually write a for function starting from a for, and you need to actually end up your for loop, right? This is just a simple loop. How you can calculate different things in a for loop? Well, you need to define the starting point of the for loop and the ending point, right? Let's say you have a variable called I. The loop is going to be started for I equal to 1, and then it's going to end at 100. Okay, so now inside this loop, if I just type I, you should be able to see how I is changing inside this loop. Okay, so let's see how is this working. Okay, let's look into the command window, right? You see that the I is started from 1, and it's going to be 100, right? And it's a counter. So I is a counter, and during your for loop, you can do a lot of things, right? Let's say I like to add to an arbitrary function. Let's say b every time of the for loop 2 values, right? And let's say b was 0 at the beginning. So if I put this in the command window, let's see. Okay, b was 2 at the beginning. It was 0, right? And then it goes to 2. Then you're adding every single interval of the for loop, you are adding 2 values to the b. So this is how you can actually march on what you need to do. Well, for the for loop, you need to have your n as your time step. So starting from the first time step to the final time step, right? And you need to have another for loop inside the first loop. This is now going to march on your space, right? And we call this I. So n, remember that we had u, n for time, and I for the space on the bottom, right? This is exactly the same thing. We are marching on time, marching on a space. So here I should be start from 1 and ends at the last space interval or breakpoint, right? And inside of these 2 for loops, you need to do your comments or calculation codes. This was just a hint. It would be great if you can try to write this for loop to find your unknown function, right? For the next time step. So this is the current time step, right? But the next time step is n plus 1 and I. So this is the question. Let's see if we can write this equation. Okay. Any question before we end the lecture? And if you had any trouble in writing all these codes that you have been working with me, just let me know. We can actually set up some other meetings outside the class to go over your code. Okay, so for next Monday, let's see if we can write this or finish or complete this line. Or to finish the entire code. All right? No question then?
All right.
Have a
Right.
great. Then have a great night and see you on Monday.
Thank
You
you,
too.
doctor.
Thank you,
Thank
Doctor.
you,
Thank
Doctor.
Thank you as well.
Thank you.
Thank you. Bye. Now I will actually put the code on Brightspace for your review. Thank you.